Welcome to our latest explainer. Today we're taking a super rapid-fire journey through the entire physics of the universe. Seriously, whether you're out for a walk, playing a game, or just sitting perfectly still right now, you are experiencing physics. So let's strip away all the boring textbook jargon and take a look at exactly how the universe operates. It's kind of a wild question, right? But we're going to zoom from the highly relatable human scale of simply putting one foot in front of the other on Earth all the way out to the dark, mind-bending cosmic abyss. And as you'll see, everything is connected by the exact same fundamental rules. So, here's our roadmap for today. First, the basics of motion. Then, forces and gravity. Next up, electricity and magnetism explained. After that, thermodynamics and chaos. And finally, waves, light, and space. All right, section 1, the basics of motion. Because, every journey really does start with a single step.
Okay, picture this. Imagine a guy who just starts walking from South America back in 1977. 500 days pass, he's still walking. 1,000 days, still walking. Finally, he stops in North America. This incredibly grueling journey perfectly defines our first two concepts: distance, which is the massive 3,608-kilometer length he covered, and time, those staggering 2,425 days it actually took him to do it.
Now, while our guy was zigzagging all over the map to accumulate that pure distance, think about an airplane. An airplane cuts a direct, straight-line shortcut right through the sky. In physics, that direct line is called displacement. It's basically nature's ultimate shortcut.
So, a plane is incredibly heavy, right? It's got a massive amount of matter, yet it arrives in just a fraction of the time. The secret there is velocity. But keep in mind, speed is really just how fast you go, whereas velocity adds that absolutely crucial element of a specific direction.
Think about a car race for a second. If every single car had the exact same velocity, well, the result is just a massive tie. Winning requires actually changing that velocity, and that is acceleration. And as Sir Isaac Newton formalized for us, changing velocity always requires the application of force.
Which brings us to section 2, forces and gravity, the invisible strings of the universe.
The universe behaves a lot like one giant seesaw. If you have equal weights on both sides, everything balances out into equilibrium. But if you have unequal weights, the system automatically triggers opposite reactions. This underlying law is literally everywhere. And it works right alongside another force we constantly deal with, gravity, which is that universal force of attraction between all matter.
But what happens when that universal tug-of-war gets kind of curvy? When gravity pulls objects not into a straight-on collision but into a sweeping arc? Well, that's when centripetal force takes over. This is exactly what Kepler's law of orbits describes. It's this profound, invisible tether trapping planets in an endless, elliptical dance around our sun.
Now, what if a force twists along a specific axis? Then you get this wild, tornado-like effect called torque. Torque is a rotational force. And as things start spinning, they are actively transforming resting, potential energy into chaotic, moving, kinetic energy.
This endless exchange perfectly shows why energy can literally never be created or destroyed. It can only be transformed. The energy in the universe is just this constant flowing loop, shifting from resting potential to moving kinetic, driving everything from a spinning wheel on a bicycle to entire orbiting planets.
All right, section 3, electricity and magnetism explained. Let's dive into the power of the unseen spark.
We generate electricity using pretty much everything from natural gas to wind, and George Ohm proved long ago that this electrical flow constantly battles resistance. But here's the cool part. What happens when current actually flows? It creates a magnetic field. We use these really elegant geometric rules to map it out. The right-hand rule tracks the curling magnetic field, while Fleming's left-hand rule maps out the intricate dance between current, magnetic fields, and physical thrust. But hey, before we even get to complex circuits, let's talk about simple charges. You can prove Coulomb's law of electrostatic attraction right in your house. Just rub a plastic comb on your hair, bring it near some tiny pieces of paper, and watch how that friction generates opposing charges that inevitably attract. It's literally the universe's fundamental push and pull right in the palm of your hand.
Next up, section 4, thermodynamics and chaos, or why everything eventually falls apart.
So, the second law of thermodynamics introduces this fancy, somewhat terrifying term called entropy.
Entropy basically dictates that our isolated universe is constantly, inevitably drifting toward absolute disorder and chaos. Things don't just naturally get neater on their own. They fall apart.
And honestly, you witness this unstoppable cosmic chaos every single day. Think about it. A solid log burns into chaotic smoke and ash. Ice melts into a messy puddle. Salt completely dissolves in water. Kernels violently explode into popcorn. You can't easily reverse any of these processes, and that is everyday entropy in action.
But even the chaotic flow of liquids and gases follows strict rules, thanks to fluid dynamics. Bernoulli's principle shows us this amazing inverse relationship. If you crank up the speed or the velocity of a fluid, its pressure actually drops. It's exactly how airplanes use the shape of their wings to lift off the ground and fly.
Finally, Section 5, Waves, Light, and Space. Let's listen to the cosmic echoes. Picture yourself standing at a train station. A train speeds by, blowing its horn. As it approaches you, the sound waves bunch up together, creating a higher frequency and a much higher pitch. But as it speeds away, the waves stretch out and the pitch drops noticeably. That is the Doppler effect. And the crazy thing is, it doesn't just happen with sound. This exact same wave bunching effect happens to starlight. If a star is moving closer to us, the light waves bunch up, shifting into a high-frequency blue. But if the star is moving away from us in our expanding universe, the light waves stretch out into a low-frequency red. We call this redshift, and it's basically the visual version of the Doppler effect. It's actually pretty humbling when you realize just how little we really see. Visible light is just a tiny, tiny fraction of the whole electromagnetic spectrum. Space is flooded with invisible waves like cosmic microwave background radiation, which is literally the lingering, detectable echo of the birth of the universe itself.
Now, if we can see something, it's because light reflects off of it. If it's completely black, there's an absence of light. But out in the deepest, darkest parts of space, gravity gets so incredibly intense that it creates a black hole, the ultimate cosmic trap. Its pull is so unimaginably strong that absolutely nothing, not even a single particle of light, can reflect or escape its grasp. So, if energy can never be destroyed, what truly happens to everything that falls in?